Hello, everyone. As Regina said, we are the team from Brigham Young University in Provo, Utah, and our presentation is entitled Predicting Stream Flow in Cuba for Water Resource Management. My name is Chris Edwards. I am a senior at BYU currently, and I will begin a master's degree in the fall.
I am Riley Hales. I'm also finishing an undergraduate degree in civil engineering. I'll be starting a master's program next year.
And I'm Jacob Lewis, also finishing my undergrad in April, and I'll be starting employment upon graduation. We'd also like to thank our advisors, Dr. Roland Hotchkiss from BYU, as well as Eric Sabilla, who helped us to refine this project. So as we begin, when we look at stream flow and water management, the reason that this is so important is because water is such a basic requirement for life here on Earth. It's something that we all need, and as such, it's extremely important for us to monitor not only the quantity but also the quality of the water that we have that is available to us. And just to kind of show the importance of this, to help create a better world, the United Nations developed 17 Sustainable Development Goals. These have been adopted around the world by 193 different nations. And of these 17, at least 11 directly or indirectly involve water quality management. And so it just goes to show how important water quality management and resources is as we look at helping to develop a better world. In Cuba specifically, with a population of nearly 11.5 million people, they typically use annually about 3.88 billion cubic meters of water. Because it's an island, Cuba has limited water coming in, mostly from storm flows, and as such, it just becomes even more important for them to be able to monitor this and know where this water is going for uses such as irrigation, drinking water, and industrial needs on the island itself. Of course, Cuba also sees the extremes of water as well. Cuba suffers from a hurricane or a tropical storm approximately every 2 years. These can cause major flooding and damage. Pictured here is Cuba during Tropical Storm Alberto, which hit last year in May. Caused major flooding. Around 3,000 people had to be evacuated and numerous lives were lost. Cuba also sees the other spectrum with droughts and water shortages. And this is where water resource management can really help to plan and prepare. Cuba has been lauded for its emergency response, and our goal is to help improve these processes. So to really effectively manage our water resources, we need three things. First of all, we need to know where the water is, things like stream beds, reservoirs, and things like this. Secondly, we need to know when the water will be arriving, and we also need to know the quantities, just to be able to manage and mitigate flooding and things like that. So once we have these, our principal goal is to help decision makers, first of all, to identify, and not only in extreme situations, but just in day-to-day use, where water is being lost and how it can be saved. And so once this has been identified, decision makers can plan more effectively and efficiently, which then allows them to respond quicker and more efficiently overall.
So the question then becomes, how do we get this information on stream flow? First off, you need people to take measurements. Currently, in Cuba, they have a system of precipitation gauges that are managed by volunteers. And additionally, stream levels and stream flow rates are measured by hand. In addition, in addition to this precipitation and stream flow data, to be able to predict stream flow throughout the country, we need to have an understanding of the topography and the terrain. This data then needs to be compiled, processed, and analyzed by engineers and scientists before it can be delivered to decision makers to be able to plan and prepare for events such as flooding. The streamflow prediction tool is a global model that covers these steps. It combines precipitation data, soil use, and terrain data to give a 15-day streamflow forecast, thus enabling decision makers to have the data they need. It automates the steps of data collection and processing so that decision makers can focus their resources on the actual decisions. The streamflow prediction tool is a global model, and global models have several benefits. First off, they take advantage of readily available satellite data, which is becoming even more higher quality and more accessible. This data is very accessible on the internet. While not substituting the need for local measurements and local data collection, it can be a viable addition, which can lower data collection costs locally. And these global models can be very useful, especially in areas where there is no measured data, there's no record, or it would be very expensive to implement a system. The streamflow prediction tool was developed at BYU with the goal of giving decision makers around the world the necessary streamflow data that they need. It is based on a model produced by the European Center for Medium Range Weather Forecasting, or ECMWF, whose meteorology is widely accepted and used throughout the world. Every day, the ECMWF produces a global runoff grid, which is the amount of surface water level runoff that will occur throughout the world. The streamflow prediction tool then routes this global runoff grid into the nearest stream, producing a 15-day volumetric streamflow forecast. For every river in the model, the streamflow prediction tool produces a hydrograph. And a hydrograph, as shown here, shows the flow rate on the y-axis over time on the x-axis. To help with uncertainty that arises in any model, the streamflow prediction tool produces a 52 forecasts each day, and this group of forecasts is known as an ensemble. And again, the forecast goes out for 15 days. Since there are 52 different forecasts, to help the users get a better understanding of the forecast, the hydrograph shows the mean forecast, the standard deviation of the 52 different forecasts, as well as the minimum maximum flows. There's also a single higher resolution model that is run each day, and this helps in areas with higher terrain variability. We'd now like to show you a brief video demonstration of how this tool works, which can be accessed online for free. Once inside the tool, you select the watershed you want to view. In this case, we'll select Cuba. This brings you to the map, and as you zoom in, you can see the stream network. We'll go into Havana. Clicking on an individual stream brings up the streamflow forecast. In this case, the different colors represent different levels of flow. The user can also select a forecast from any day within the last week. And again, this graph is the one I just explained. It shows the average of the 52 forecasts for that day, going out 52 days, along with the maximum and the minimum and the standard deviation. This data, the forecast data, can be downloaded by the user as a CSV file for their own use for each individual stream. The tool has some additional features, and one that we'll show you in this video is a graph of the daily average flows for every day in the year. And this allows the user to see whether today's forecast is above normal, if it's low. So the streamflow prediction tool helps water resource managers have access to the data they need, all combining data collection, terrain processing, all in one thing, so they can focus on data collection, focus on decision making and preparing for flood events.
And this kind of information can be incredibly valuable to both engineers and decision makers. I'd like to discuss 3 specific ways this information can be applied. The first is some historical information. This hydrograph pictured is like the one you just saw in the video, except you'll notice on the x-axis, instead of going 15 days into the future, it shows 35 years worth of historical information. This is generated more or less the same way as the forecast information. Again, taking advantage of the global sources of data available for meteorology. Going back 35 years into the past, we have historical data and can produce those same runoff grids that is processed, routed to streams, and turns into streamflow, produces this hydrograph. This is very valuable for retrospective analysis. Knowing when and where and how much those questions for the past helps us for the future as well by providing context. You can analyze well-documented floods with the simulated stream flow that occurred during those same periods, helping you understand if a certain flow is going to cause damage or what kinds of things you should expect. The second application of this data is a piece of software developed as a collaboration between Brigham Young University and INDRI, which is the Water Resources Department of the Dominican Republic governments. The tool provides a series of simple interfaces like this one pictured. The application draws the predicted streamflow values from the streamflow prediction tool and puts it in this table, where the user can then specify how much water they expect to use out of their reservoirs. Then using bathymetry information, the app can calculate differences in elevation just by using the predicted streamflow values and the predicted outflow values. Last is an application used for flood mapping. Engineers are really used to seeing graphs like this one, the hydrograph, and that shows you flow versus time. However, it can be very difficult even for an engineer that's familiar with this to turn it into something practical that a decision maker can use to prepare. This is a flood extent map that will show you the boundaries of where flooding occurred. This application works very similar to the streamflow prediction tool. You start by just picking an area of the world and the dates of the forecast that you would like to analyze. Then you zoom into the area of the map that you're interested in. This time when you click on the stream, instead of getting those same graphs again, it uses the global elevation data and the other satellite data that we have available to produce an animation that shows where flooding will occur versus time. This uses those same predicted streamflow values as the tool shows on the hydrograph. Additionally, since there are 52 different estimations in the ensemble, there's uncertainty in what we do. The tool also plots a similar animation, this time instead of showing where the flooding will occur, showing the probability of experiencing flooding within those extents versus time. So where does that leave us for Cuba? We have the streamflow prediction tool. This has already left its research and development stage and is now housed by the European Center for Medium Range Weather Forecasting. The information is available every day as soon as the runoff grids are computed. Additionally, there are the derivative applications like the ones I've shown and as many as 20 others. These are available for free. Most importantly, engineers could start using this today. You don't need subscriptions, you don't need technology, you don't need anything besides a computer that can access the internet. This is readily available as a web service intended to help decision makers. In the future, we propose a partnership between Brigham Young University and Cuba, thereby connecting Cuba to the larger international community that works towards sustainable water management. As the original developers of this tool, we can give you the capacity to use global models. We can show you the benefits, train you in the software and how to access the data, thereby enabling you to save time and money and lives and infrastructure and things that are going to make a real impact in the day-to-day lives of Cubans. By forming this partnership and joining the international community, Cuba can become a player in the fight for a sustainable world. Those sustainable development goals can't be accomplished by the United States alone any more than they can by Cuba alone or any individual country. This collaboration and teamwork will lead us towards that. We believe that by sharing resources and everyone being a part will lead us towards the sustainable water management and sustainable world at large. Thank you.